Hello everyone, my name is Eduardo, and in this research I will characterize the internal tides in a region of dynamic meso and submeso circulation in the East Australian current at latitude of 27 degrees south. So basically, internal waves are waves that oscillate within a stratified fluid, and this figure represents three different mechanisms of generation of the internal waves. First one, it is the focus of this research. It is the internal tides, which is caused by the tidal flow over steep topography. The second mechanism, it is the inertial wave, which is caused by the Coriolis and wind force. It's the combination of both. And the third one is internal lee waves. It's caused by the quasi-steady flow over rough topography. In our research, as I said, we're going to focus on the internal tides. Internal tides, they can propagate away from the side generation and fill the global ocean. And they are very important in mixing of the layers that modulate the Earth climate. And also they are very important in mixing of the layers near the bottom of the ocean as well. And here you can see the internal tide propagating through the bottom and goes on through until 1,000 meters depth. So they are very important in bringing nutrients to the water column and which affect the biological productivity. And few studies occur. We have few information about the internal tides in the Eastern Australia. So that's the motivation of our study. First, we characterize the internal tides and separate it into diurnal and semi-diurnal. Second, we have an insight of the origin of the internal tide, if it is local or remote. Thirdly, we analyze the influence of the frontal eddies on the internal tide. Then we analyze the mesoscale eddy influence on the internal tide. And then I will show a case study of the inertial wave, that is the mechanism of generation of the inertial wave in the study area as well, in just a case study. So basically, to characterize the internal tide, we use 7 moorings deployed off of Brisbane from May 2012 to June 2013. The moorings were deployed from the continental shelf, the board of the continental shelf, until more than 4,000 meters depth. And we use sensors of temperature, salinity, velocity, and pressure to analyze the internal tide. And this is the location of the moorings. So firstly, we analyze the spectral energy of the raw data. With that, we can see the main constituents of the internal tide, the harmonic constituents of the internal tide. So basically, the internal tides are composed for different harmonics, and they are separated into diurnal and semi-diurnal. So here is the diurnal. We can see that the diurnal is stronger, and it's composed by the harmonic K1 and harmonic O1, and the semi-diurnal is composed by the solar harmonic S2 and the lunar harmonic M2. So that's the first characteristics of our internal tide. We separated into we filtered the data into diurnal and semi-diurnal differently, and we analyzed this data separately now. And we can see that the diurnal and semi-diurnal have strong peaks of the internal tide near the bottom. So that's very interesting and important for mixing the bottom of the ocean. So we calculated the spectral energy for the entire cross section for all the sensors of the moorings. And we can see that the diurnal is stronger than semi-diurnal. And also it's stronger above the continental slope. So that's another characteristics of the internal tide. And now we would like to know where this internal tide is being generated, if it is locally above the continental slope or if it is coming from a distant place. So for that, we compare here the temperature anomaly of the internal tide with the barotropic tide height. So we can see that the semi-diurnal internal tide doesn't have a spring nip cycle. And also the peaks of the semi-diurnal tide occurs at the nip tides. So that's one indicative of remotely generated. Another indicative it is that the phase of the internal tide is not similar, is different than the phase of the barotropic tide, which is the dashed line here. And this is another indicative of the internal tide it doesn't match with the barotropic tide, so it's not locally generated. And also the criticality is lower when compared to the diurnal internal tide. So those conditions makes me conclude that the same diurnal internal tide are remotely generated. And second, Alford et al., they are coming from New Caledonia, Solomon Islands, and New Guinea, and they propagate until here, long distance. So that's very interesting. And another thing was the diurnal internal tide seems to be local generated because it follows pretty well the spring neap tide. So the peaks of the internal tide are on the spring tides. So that's indicative of local generation. Also the phase of the internal tide above the continental slope, it is close to the phase of the barotropic tide. So it's another indicative, and the criticality is higher above the continental slope. So we can conclude the diurnal internal tide are generated above the continental slope. And also that the diurnal internal tide is variable over time, temporally variable. So next step now we would like to see what is causing this variability of the internal tide. And we realize that most of the peaks of the internal tide has a presence of a cyclonic eddy passing through the study area. So we have a look closer at the cyclonic eddies, and we can see that they happen very often. This is a snapshot that we can see 4 cyclonic eddies passing through the study area, and they are called frontal eddies because they are submesoscale cyclonic eddies, about 30 kilometers. So how the cyclonic eddies can influence the internal tide? So one mechanism that could be happening that we analyzed was the stratification, because the internal tide above the continental slope depends on the stratification and the tide. So we analyzed the stratification, and we saw that most of the peaks of stratification are related to the peaks of the internal tide, also strong correlation between them. So we conclude, and we have a look. We use output model to analyze the internal tide, and see what is causing this strong stratification above the continental slope. So basically, the stratification is caused by this front of the eddy that creates a horizontal gradient, and also a strong stratification in this area. So we can see here the moment of this eddy is here. We can see a strong horizontal gradient of density, and here we can see the strong stratification that occur at this period on 7th of March. It's a strong stratification close to the surface as well. And here is the average, it's a mean between 2012 and 2013. And we can see that the stratification normally is not that strong and it's not that deep as well. So that is a very good indicative that that's the mechanism of generation of the internal tide. The cyclonic eddies increase the stratification. So we can see here 2 cycles of tide, one with no passage of an eddy and another one with a passage of an eddy. And we can see that the eddy increased the stratification. The eddy is in black, the eddy kinetic energy, and the stratification is in gray. So simultaneously increase the stratification and at spring tide, and then we have intensification of the internal tide. This is the pressure of the internal tide, temperature, and vertical velocity of the internal tide. So we can conclude that the cyclonic eddies are responsible for change the stratification above the continental slope and increase the strength of the internal tide. Another mechanism that I analyzed was the mesoscale, the influence of mesoscale eddies on the internal tide, because second Lelong and Kunz, the if the eddy has the same scales of the barotropic tide, they can interact. And the scales are basically the same velocities, similar velocities. So the eddy has to have similar velocity of the compared to the barotropic tide, and the same wave number, the same length scales of the internal tide. So we analyze both characteristics and we choose an eddy that seems to have that characteristics, principally on the velocity, that's the eddy. And we could see that there were an increase principally in horizontal velocities, horizontal scales of the internal tide. This is the internal amplitude of the internal tide, and this is the characteristics of the eddy. So we can see the stratification, uplift here, and the intensification of the horizontal scales of the eddy, and no intensification of the vertical scales. That's very characteristics of this mechanism of interaction. And we can see that the barotropic tide has similar velocities of the eddy field, and this is the time series, and this is the time series of the internal tide. So that increase exactly on the spring tide as well. So, and in the end, and also the wave number of the eddy field is similar to the wave number of the barotropic tide. They have the same, they have energy in the same wavelength. So that makes me conclude that there is interaction between the eddy and the barotropic tide that intensify the internal tide, principally the horizontal scales. And here we can see the time series of intensification. And to finish, I did a collaboration with Scripps in San Diego, and we analyzed the inertial wave. So I will show just quickly how we analyze this mechanism. Basically, the wind force, the wind, basically we found a moment of strong wind stress, and this wind are rotating, so there is a strong vorticity, and there is a strong internal wave as well. So we analyzed this moment, and we could see that that wind is generating an inertial wave here. This is very characteristics of an inertial wave with strong wave on the surface, and also it propagates until the bottom as well. So that's very interesting, and that's our next step. So thank you very much. Thanks for watching. If you have any questions, just let me know.